So now that we've established how to find a plane, we need to talk about the different relationships between distinct planes. And in particular here, we are going to be focusing on parallel and orthogonal planes. So to get us started, I want you to note that the normal vectors of distinct planes tell us about the orientation of each plane and their relationship. So to begin, we want to look at the definition of parallel planes. So we say that two distinct planes are parallel if their normal vectors are scalar multiples of each other. So two distinct planes are parallel if their normal vectors are scalar multiples. So in other words, if we have one normal vector, so this is the normal vector of our first plane, if that is a scalar multiple of the normal vector of the second plane, then those planes are parallel. And that's, of course, where C is our scalar multiple. So this is what we're going to use to test if two planes are parallel. So graphically, looking at this illustration here, we have plane number 1 with the normal vector n sub 1, and we have plane number 2 with the normal vector n sub 2. So looking at this graph, let's assume that this here is a normal vector for the first plane, and we'll label this n sub 1. Now, if we find that the normal vector of your second plane is a scalar multiple of this normal vector, then those planes are parallel. And so we can say in this case that n sub 2 is equal to some scalar multiple c of the normal vector n sub 1, therefore making these two planes parallel to each other. And case number 2, here we are considering what makes two distinct planes orthogonal to each other. So we say that two distinct planes are orthogonal or perpendicular or normal if their respective normal vectors are orthogonal to each other. So if their respective normal vectors are orthogonal. So how are we going to be able to test this? Think back to our vector operations. How would you check if two vectors are orthogonal? The dot product. We know, of course, that if the dot product of the normal vector of the first plane dotted with the normal vector of the second plane is equal to 0, then those vectors are orthogonal, thus making the planes that they correspond to orthogonal. So this provides us with a nice way to check if two distinct planes are orthogonal to each other. So let's go ahead now and consider an illustration of this. So again, let's let plane number 1 have a normal vector n sub 1, and we'll let plane number 2 have a normal vector n sub 2. So looking at plane number 1, let's go ahead and say here is its normal vector, vector n sub 1. And of course, this is intersecting that plane at a 90-degree angle. And then we'll go ahead and we'll say here is the normal vector of the second plane, vector n sub 2. And again, this vector is intersecting that plane at a 90-degree angle. Now, if these two vectors, n sub 1 and n sub 2, are also intersecting at a 90-degree angle, then this means their dot product is 0, the vectors are orthogonal to each other, and therefore the planes are also orthogonal planes. Now the last thing I want to point out to you before we move on to look at examples is this line here where the two planes are intersecting. This illustration provides us with a nice graphical representation of the line of intersection. So as we say, we could have parallel planes, we could have orthogonal planes, or we could just have planes that intersect each other. not necessarily at a 90-degree angle. So this L is our next point of interest. This is the line of intersection between two planes. So keep this illustration in mind as we proceed. And let's go ahead now and look at some examples.